Okay. So, what we have done so far in the last class is that we are trying to characterize the band pass noise, right. And for that target we have actually devised a circuit and we are trying to evaluate the transfer function of that circuit, right. So, by exciting it with a delta function, we have first proven that that particular circuit is a linear time invariant circuit. And then we have proven actually derived the transfer function of that circuit, and we could prove that it is just nothing but a band pass filter. Okay. And then we could show that if a band pass signal exactly matching with its band, if it is passed through this, it will remain same. Okay. So, that is why x t, if that is a band pass noise exactly matching with its band, then at the output also it will remain as that. And then we could say that okay, then x t can be represented because of that circuitry, can be represented as some x c and x s in phase and quadrature, right. So, that is something we have proven. So, therefore, finally it came to that x t is x c t cos omega c t plus x s t sin omega c t, where we know that this x c t I can actually trace back them in my circuit, the circuit we have shown. So, x c t is nothing but equivalent to B 1 and x s t is nothing but B 2. Okay. So, we already know that what they are. Okay. So, now let us try to see what is the characteristics of this x c t. So, x c t, if we just trace back through this circuit, it is nothing but this x t, okay, multiplied by this and then passed through a low pass filter, ideal low pass filter, right. That is actually B 1. So, I can write that as 2 x t cos omega c t, we are again taking theta to be 0, okay, because it is valid for any theta. So, I can always take theta equal to 0. So, this is x c t passed through a ideal low pass filter, as long as my x t is band limited. Okay. So, basically the x t is limited to minus b to plus b within that f c, then if I just multiply it with cos, so it will actually come down over here, I will just take that low pass portion of it. Okay. So, it remains this, only we have to make sure that it is within that band minus b to plus b. Okay. So, that is actually x c t, which is low pass equivalent. Of course, it has to be passed through a ideal low pass filter, and x s t similarly should be 2 into x t sin omega c t, right. So, let us first try to see this one. So, what happened, my x t, suppose that looks like something like this, let us say this is f c, it must be symmetric, so something like this. Okay. So, let us say this is minus b minus f c, or I should say minus f c minus b, and this is minus f c plus b, that point. Okay. So, this is actually my 2 b. Similarly, this is f c plus b and this is f c minus b. This is my 2 b. Okay. So, now if this is x t, what is x c t, the in phase component, that is nothing but this x t multiplied by cos, and 2 is there because whenever I multiply by cos in the spectrum, if I wish to see, there will be a half term. So, that will be cancelled out. So, it is just whenever I multiply by cos, this whole thing will be shifted to plus f c and minus f c, right. Once I shift this particular thing, once I shift to plus, this will come over here, and this particular term will go to a very high frequency 2 f c, and when I shift to the other side, this will come over here and this term will go to minus 2 f c. Those things will be anyway cancelled because there is a low pass filter. So, what will remain over here at the center is something like this. From minus b to plus b, this particular pattern will be repeated, and from this to this particular pattern will be repeated, right. It is the addition of these two which will be the xc. Okay. So, or if I just take a Fourier transform of this, so Fourier transform, let us say it is x, let us say xc or xcf, right. So, what that should be? That should be actually x f plus fc, f minus fc. So, original f plus fc plus x f minus fc, but this must be defined for a f where mod f less than equal to b, okay, which is just like this. All the higher frequency term will be neglected, it is just these two part will overlap and whatever I get. Okay. So, that is actually my xct and corresponding Fourier transform of that. Okay. So, I immediately get the corresponding Fourier transform of this one, right. It is very easy to get directly the Fourier transform as long as I know the xt means the power spectral density. So, basically what I can do, instead of doing this, I can relate them in terms of power spectral density. So, I can write Sxcf, which will be just this, whatever Sx, suppose Sxf is known, that is for the xt I know its average Fourier, means average power spectral density. So, this should be multiplied by 2 cos omega ct. So, therefore, it should be that Sxf must be shifted to plus fc minus fc. So, I can write Sxf plus fc Sx f minus fc, and then I have to put this condition that mod f less than equal to b, right. It should be this, and then for, because it is power spectral density, so therefore, for cos there will be a half term which will be squared. So, there should be a 1 by 4, and there is a 2 term already that should be squared. So, it will be 4 gets cancelled. So, this happens to be my power spectral density of Sxcf. Okay. So, without going into the autocorrelation or cross correlation function, I directly define my power spectral density. As long as xt is defined, I can always get the corresponding xc, that is the in phase term, his power spectral density. Similarly, Sxsf also will be same, because whatever sign is there, it does not matter when you take power spectral density, it will be squared and all other things will be cancelled, it will just be plus again, f plus fc Sx f minus fc, again defined for this. Okay. So, immediately I can see the power that we wish to evaluate. So, if you just try to calculate this power, that must be the integration of this one over the whole spectrum. Okay. So, this is just defined within B. So, it should be this plus this. Okay. So, Sx plus Fc within this and minus Fc within this. So, that should be the power of this. Similarly, Xs squared t also have, because they are having same similar power spectral density. So, it must be same, and not only that, this is also same as this, because think about these two power spectral density. So, if I just go back to this example, what is happening? The power spectral density of this one will be this plus this, same thing happening over here. It is just this portion is being repeated over here, this portion is being repeated over here without having any attenuation. So, the power spectral density will be just addition of these two, which is same. So, therefore, the overall power remains the same for the in phase component, for the quadrature component, as well as the random process that we are talking about. This will be always happening as long as the bands are properly adjusted. Okay. So, therefore, what we have seen so far is we have seen how do we actually evaluate a band pass random process through equivalent to low pass random process, which are called Inphase and quadrature component. Okay. So, that XCT and XST, and we have also seen the interrelationship between their power spectral density. Okay. So, that band pass process, how the XCT can be related to the corresponding XT, that is something we have seen, and we have evaluated their power also. Okay. So, this is something we have already done. Now, what we wish to do is something like this, that we want to evaluate the cross correlation of this XC and XS. Now, we have two things. So, this XCT and XST plus tau, okay, which is nothing but R XC XS, okay, if it will be stationary. So, what will be able to prove that this will be just 0. Okay. So, for that you just have to take this relationship XC and XS and follow through the means you know already the autocorrelation function of Rx, just go through that, follow the steps, you will be able to prove that this is 0. So, basically this means they are uncorrelated, they are incoherent. This is something we will be always able to prove. Okay. So, that is another thing which will be probably means heavily required for our analysis of noise. So, whenever later on you will see, whenever we have a band pass noise that is coming out because of the band pass filtering, we will be always writing it in terms of Inphase and quadrature, because once the noise comes in, it is the noise plus signal which goes through the whole demodulation process. So, we have to actually take the signal as well as noise going through the demodulation process. So, if that has to be done, then I need to have a representation of the noise. So, that is the representation of the noise, that NT, suppose it is noise which is a random process, that must be NS T sin omega Ct plus NCT sin cos omega Ct. So, always I will be able to write that way, and then I also know their corresponding power spectral density, their cross correlation, all those things we know already because we have characterized them already. So, once all these things are known, you will be able to see that we have a strong tool set which will give us some analysis. Okay. So, all we are trying to do over this exercise, that definition of random process, what is stationarity, how do I get power spectral density, what is autocorrelation, and then if I have a low pass noise, band pass noise, what are the corresponding representations. So, all these things we are doing just to aid ourselves to do noise analysis of the system that we have already discussed so far, all those different kinds of amplitude modulation systems. Okay. So, we will just give two more things which will complete this entire discussion probably. So, those two things we will just discuss briefly, and after that we will give you an outline of how we actually can do noise analysis. So, let us just first try to see, go back to our noise which was something like this, right. So, we want to characterize that noise, so which is having a strength of eta by 2, right. Now, this noise is passed through a band pass filter, okay, centered around Fc, and band is 2B, similarly minus Fc, band 2B, right. How the noise will look like after passing it through that? So, it will be a band pass process. So, that should look like this. So, it should be still, the strength should be eta by 2 because these are all 1. So, mod Hf square will still remain 1, pass through this, we have already proven that it should be mod Hf square into the input noise is eta by 2. So, we just multiply that and we should get this, right. So, that strength should be eta by 2, okay, defined at minus Fc plus Fc and within this band of 2B. So, what is the noise power? So, let us say this noise is defined as xt. So, x square t, that must be integrated, noise power is just integrated over this entire band, okay. So, which is nothing but eta by 2. So, 2 into integration from this to this, right. So, that is nothing but 2b into eta by 2. So, that is eta into b 2 times. So, that should be 2 into eta into b, that is my overall noise power, right. Now, let us see what is my XCT. So, what is XCT? XCT must be this shifted to this and this part shifted to this. So, therefore, how much I do get? It should be band limited from minus b to b, but this one will be shifted and this one also will be shifted. So, overall strength will be eta by 2 plus eta by 2. So, that must be eta. What is the power of this one? So, XCT square bar, that is also 2 eta into b if I integrate over this, which we have already said that this and this power will be equivalent. Similar things will be happening for XST as well, right. For XST also same representation will be happening and I get 2 eta b. So, that is how we will be evaluating the noise power and will be evaluating the corresponding power spectral density of noise whenever we have a noise. Okay. So, in our noise analysis we will be taking the noise as this, which is a flat spectrum, okay, and whichever filter we will be employing, be it low pass or band pass, we will be always taking them to be ideal, because if you do not take ideal then probably the analysis will become too much complicated. Okay. You can always do that, but just to see the performance probably for both, means if I wish to compare performance of two systems, I will take ideal filter for both of them and then try to analyze it, because it just becomes, life becomes much more simpler. Okay. So, that is something we will be trying to do. Now, let us try to talk about another thing, okay, which is called that noise we are characterizing. What is that noise? You might be hearing this particular term so often, that the noise is AWG, okay, or AWGN, or the channel is called as AWGN channel. Okay. What do I mean by this? The first term is called the additive. It is just defining the noise, right. That means I have already assumed that noise either is generated in the channel or in the receiver circuit, whichever place it is being generated, it is then passing through, the channel will be linear and the circuit also will be linear. So, as long as they are linear, so basically the noise will be just added on top of signal. So, it is a additive noise, not multiplicative or any other kind of noise. So, it is just additive noise. So, you will be always assuming that if I have signal, the noise will be just added to it. Okay. So, that is the first thing, additive. Then the next term called white. So, the noise that we have characterized, which is probably the most random noise that we know, which has an autocorrelation function of impulse and corresponding spectral density which is flat. This is what characterizes it to be white. That means it has all the frequency component equivalently with equivalent strength. It just comes from that concept of white light. So, what is white light? That it has all other lights or all other wavelength that characterizes different light, either it is violet or blue or any other things. So, all those are equally added to create white light. Okay. So, same thing, the white noise is being created by equivalent noise component at every frequency, as many frequency component you can think of up to infinity. So, all those frequency components are equivalently present in this particular noise. And because the noise is like this, it just comes from the autocorrelation function of our understanding. From there, because it is like this, that every frequency component are equivalently present, we call this as a white noise. So, most of the time we will be considering white noise. The next part is G, which is the Gaussian. Okay. So, what does this means? This actually says that See, this is the power spectral density, this is the autocorrelation. Actual noise will look like something like this, right. And it will, because it is a random process, you can have different such samples, okay, infinite number of such samples which will look different if you take different samples. Fix any instant, it is a stationary process, we have already talked about that whatever that noise is, that is already stationary. Okay. So, any time you pick, I know that the statistical property does not change. Okay. So, if I just pick this time instant or this time instance and try to take these samples, put a PDF, and what I will observe that this is following a Gaussian process. We have already discussed about Gaussian process, and that is why we have discussed Gaussian process, because it is so important that most of the things probably we have not discussed one important property of a random variables, that if you have many number of independent random variables, means infinitely many, and if you just all of them are independent, if you just add them together, the PDF that you will be getting, that always goes towards Gaussian. Okay, that is called the central limit theorem. We have not discussed that, but in probability theory you will be learning those things. So, because of central limit theorem, we know that always a process which is constructed of many infinite independent processes will tend towards Gaussian process. So, the noise is generally being generated by infinite number of things which are naturally happening inside the nature. Okay. So, because they are all independent and they are all adding up to create noise. So, we can all very safely say that it follows central limit theorem, and the noise process will have PDF which is Gaussian. So, that is why this noise generally is taken to be Gaussian. Okay. So, what does that means? That any sample time you take all the ensemble, put them in a histogram, normalize them, whatever PDF you will be getting, that will look exactly like Gaussian PDF with a particular sigma square, okay, which is actually the power of that, right. And that sigma square of that Gaussian should be equated to the power that you are calculating from the noise. Like for this band pass noise, we have evaluated this 2 eta b is the noise power, that must be the sigma square of the corresponding Gaussian, because the Gaussian process has two things, one is mean and variance, these two has to be specified. So, variance is specified, and all these Gaussian noise are generally, because they are created by random process which can means either create positive voltage or negative voltage equally likely. So, it is often having 0 mean. Okay. So, always the signal which is characterized by noise signal will always have 0 mean. So, we can always say that it is always characterized by a Gaussian process which has 0 mean, and the sigma square is just equivalent to the power that we are exerting, okay, the noise power we are thinking of. So, that noise power will depend on that power spectral density of it and the band we are operating at. So, accordingly we can, the way we have calculated noise power, we will be getting that power, and that sigma square will be equivalent to that power, because these two are means exactly equal. Okay. So, that is why whenever we talk about a particular channel and a noise process that is being added, we always take help of additive white Gaussian noise. There are other noise for different system, like in an optical system probably it will not be similar things. Okay. So, because of photon counting and that counting process becoming Poisson. So, there will be different kind of noises which can also be added, but generally speaking most of the receivers are being analyzed with respect to additive white Gaussian noise. So, that is why it will be very important that we know this, all these terms. So, whenever we will be because of this presence of this noise, whenever we will be characterizing noise, we will always say the noise amplitude will be just directly added to the signal amplitude, nothing else, it is additive. Okay. And the noise power spectral density will be flat with a means power spectral density specified as eta or eta by 2, whatever you like, and the noise statistics or the PDF, if you just take a particular time instance, freeze a time instant and take the PDF, you will always get that to be Gaussian. So, these are the criteria which will be always fulfilled whenever we concern ourselves with respect to the noise that we are analyzing. Okay. So, this is one thing I wanted to characterize. The other thing I wanted to say that this in-phase and quadrature representation that we have done, that is not unique. So, let us try to appreciate that part. You remember we had a we were just trying to show that suppose I have a band pass signal or random process which is characterized like this. Okay. And this is the band where it is defined. Now, I want to have a quadrature and in-phase representation. What I will do first? I will choose a FC. Now, carefully check, I can choose the FC over here, I can choose the FC over here. Okay. Once I choose the FC over here, what I have to make sure that the entire signal means that XC, if I wish to represent, that my bandwidth will be represented in such a way that the entire signal comes under that band. So, accordingly I will be defining my band. If my FC is over here, then I will have to define my band accordingly. Once I define a FC and corresponding band, then immediately if you try to represent the XC or XS, that will look different, definitely, because they will have a different kind of shape which will be translated into the central frequency. So, there is no unique representation of these two things. Okay. So, whenever we talk about that in-phase and quadrature component, it is not by definition unique. It just depends on where you put your FC, that central frequency, because you will be given a band pass equivalent signal. Nobody will tell you with that spectrum that this is the central frequency. That is according to your choice. You can choose a central frequency, accordingly you will have to adjust the band. And once you adjust this band and central frequency, there will be a definite XC and XF which will be created, and this will keep on changing as you change your XC and FS. As you have seen also, that particular circuit we have drawn, that is completely the transfer function of that circuit depends on what cos omega Ct we give. If we keep changing that omega c and what kind of bandwidth we put for that middle low pass filter, that HOF, if we change these two, the representation accordingly will change. So, be very careful whenever you are representing it, that you should understand that there is no unique representation, it just depends on your FC definition and the band definition. As you define them, accordingly your XC or XS will be changed. I can give you a very simple example, the one we are doing, that band pass noise, this was my FC by default and this was 2B, right, and this was minus FC and I was having this. Now, suppose I do not do that, I define a FC over here. So, then the band has to be taken as this, that will be 4B, and then if I translate this, what will happen, the overall band will be from minus 2B to plus 2B and the strength will be just eta by 2. Earlier what was the representation, because I have defined it at the central. So, the representation was from minus B to plus B and the strength was eta, right. So, you can see already there are two different representation as I defined my FC differently and accordingly corresponding band. But the overall power, if you wish to calculate, it will remain the same. So, the noise power and the associated in-phase and quadrature component, whatever you define, their power will remain the same. It is just the spectral property will change due to your definition of FC and 2B. So, I think we have almost finished our discussion of random process, and we are now almost ready towards jumping into noise analysis. So, what we will do in the next class is we will try to see how the what should be our way of doing noise analysis, because whenever we do noise analysis we want to compare two systems, that suppose DSBSC and amplitude modulation, how they perform in terms of noise. Can I say this is better in terms of noise okay, or in terms of noise cancellation. So, how do we actually benchmark them? What is the criteria to do that? How we evaluate our things, so that we can actually compare two processes. So, first we will say that, with that we will have a process which will be created, means for evaluating these particular modulation schemes, and then we will go on analyzing those modulation schemes. Okay. Thank you.